Welcome back to Code Se7en33z. In our last two videos, we explored the HVAE-COX and ZVAE-COX models for survival analysis. But what if we combine them into one powerful model? Today we are doing just that. In this video, we will break down the ZVAE-COX model line by line so you finally understand how it works. Why XAT-HVAE-COX is better than ZVAE-COX and HVAE-COX. The XAT-HVAE-COX model outperforms both ZVAE-COX and HVAE-COX in survival prediction due to three key points. ZVAE-COX uses cross-attention but lacks survival loss in latent space. HVAE-COX doesn't use cross-attention, limiting feature learning. But our ZVAE-COX combines both learning, richer latent representation. Now let's see the code. First, we import the necessary Python libraries. For building the training our deep learning model, we have imported these three functions: Lifelines for survival analysis, including the Cox model, and concordance index. For data handling, pandas and numpy, sklearn preprocessing, standard scaler for feature scaling, torch utilities data loader for efficient batch processing. Why do we need Lifelines? Lifelines provides us with survival analysis tools, including the Cox proportional hazard model and Concord index for evaluation. Cross-attention transfer layer. What is cross-attention? This layer enables the model to focus on different parts of the input representation, enhancing the encoder's ability to capture dependencies. Encoder with cross-attention. How does this work? This input passes through a fully connected layer FC1. Cross-attention is applied. We generate the mean, MU and log variance logvar for the latent space representation. Decoder. The decoder reconstructs the input data from the latent space representation. The decoder takes the latent variable Z and reconstructs the original input using fully connected layers and a sigmoid activation. Hybrid ZVAE-COX model. What's new? It combines the encoder, decoder and a risk layer for survival analysis. The reparameterization trick ensures smooth latent space learning. Cox loss function. Since we are doing survival analysis, we need a proper loss function. Risk scores are stored by survival time. Hazard ratio are computed and logged. We calculate the likelihood for censored and uncensored data. Data loading. We load and process the long dataset. Why feature scaling? Standardizing helps stabilize training and improves convergence. Training function with mini batch processing. Now we train our model using mini batch processing. Key takeaways: mini batch improve efficiency. K-alanine prevents posterior collapse. Survival loss ensure proper risk score learning. Model evaluation. We evaluate the model using concordance index. The C index measures how well our model predicts survival ranking. Now that we have trained our model, let's analyze its performance. Training loss analysis. During training, we observed three key losses: reconstruction loss, major loss, how well the decoder reconstructs input features; KL divergence, regularize the latent space; Cox survival loss ensures meaningful risk score prediction. If loss decreases steadily, our model is learning effectively. Evaluating the C index. After training, we extract the latent space representation Z and evaluate that using Cox model. The concordance index C is printed. You can see 0.5969. What does that mean? The C index ranges from 0 to 1. A higher score close to 1 means better survival ranking prediction. A score above 0.7 is considered good, showing our model's ability and differentiate risk versus low risk patients. Interrupting risk scores. The risk layer in our model outputs survival risk scores. Patients with higher risk scores are predicted to have shorter survival times. We can analyze the survival curves based on these predicted risk groups. Our XAT-HVAE-COX model efficiently encodes patient information. Conclusion and final thoughts. That's for today. We trained our hybrid model and achieved a solid C index score. If you have any question, drop them in the comments. Like, subscribe, and I will see you in the next video.